but also that PDF on simple linear regression on Moodle will show you everything that we did in class, and then some additional things with the little data set that they have in there that I'm going to have you guys use for today's example. Okay, so give it just a couple more moments here and we'll go ahead and get started. All right, let's go ahead and get started by taking a look at, yeah, this is the PowerPoint that is on there, on Moodle that is, and just want to walk you through this. So what we're looking at right now is something called simple linear regression, and really it builds directly upon correlation. So correlation is this statistic that tells us not only are two things significantly related or not, but how strongly those two things are related, and it's on a standardized statistic called R that ranges from -1 to +1. Well, what linear regression is doing is it's extending the concept of that, but breaking it down into finer grained detail. And so in correlations, you're looking at a scatter plot as a graphical depiction of a relationship between two variables. If we were to draw a pretend line that minimizes the points between all the dots, like if we would say, okay, what is the best line here, a best fit line that would minimize the difference or the distance between these dots, that is called the best line, the line of best fit, or the regression line. And so what is trying to be estimated here in a regression analysis is the line of best fit that is calculated for minimizing the differences of each individual dot here, the actual observations from the line of best fit here that you can see in the middle. So we are looking here then at a positive correlation, right, between number of prior arrests and number of future arrests, and this scatter around the line is considered error from the regression line. And so this is a sampling of the population of what we think is a representation of what's going on in the population based on this sample, and this is the line of best fit. So that's graphically what we're trying to do in simple linear regression. What does that do over and above correlation? Well, it tells us, for example, how many future arrests we might expect given any given number of prior arrests. And so for every unit increase in X, how much does Y change? That's what regression can tell us. And what impact does X, so what impact does prior arrests have on future arrests in this case? So you might find that future arrests are increased by 0.5 for every additional prior arrest. So like it would take 2 prior arrests to estimate or to predict one future arrest at some later date. And so that's another question that regression is answering us, or providing us answers to. And then you can also say, okay, what is the predicted value of y? So the dependent variable is often labeled y, and so what is the dependent variable predicted to be when the x, the independent variable, is some value? So in the case of future arrests being predicted by prior arrests, if we have so many prior arrests, how many future arrests can we expect in the future based on the observed data? Okay, so that's another thing that regression is doing. And then it also is telling us how much of the variation in y does x explain. That is, in the future, past criminals will vary in the number of times that they're rearrested. Okay, so just knowing their prior arrest record alone, how much of the variation in future arrests is explained by variation in prior arrests. And so this is what we will call later R square, or the coefficient of determination. And this is a really important stat because it tells you how well something predicts something else. And so it might say in this example, it explains 50%. Future arrests, prior arrests explain about 50% of the variation in future arrests. And so you can make that kind of statement with regression as well. And so it does all these things. It makes predictions. It tells you how much of a change in y can you expect from a change in x. And so and how much you can expect y to change given some set value of x, and how much of the variation can be explained in y given x. So just want to go through what the formula looks like. We're going to be working with this today in our exercise, but the basic formula for regression, for simple linear regression, is y, which is the predicted outcome for the dependent variable. So in this case, it would be future number, a number of future arrests. And that is set equal to a, which is a constant, which is like the number of arrests that everybody starts with on average. And then to it is b, or the slope term. So how much do future arrests go up by for every prior arrest? And then you have this x variable that will fill in for, and that is, in this case, the number of prior arrests. And so when we do the regression equation, a is given to us by the constant, b is given to us, and then we have to plug in a value for x. And that's really all we're doing when we solve for the regression equation in our homework examples. We're plugging in values for x. So you can say, okay, given x number of priors, how many future arrests can we expect given the data trend? And so you would plug that in, and then that number of priors is weighted by the value b, and then to that is added the constant a. And so that is how the regression equation is solved. It's really no more difficult than that. You're just plugging in values for x, and the values for a and b will be given. And so this a term is also known as the y-intercept. It's where the slope intersects or intercepts with the y-axis. Okay, and so that's what a is also referred to, and b is the beta coefficient, or the slope term itself in this equation. And then again, x is the variable that we plug values in for, and then y is what we get as a result as solving this equation. And so that's the regression equation. So it's just y equals a plus bx. That's all. The subscripts y here are just telling you that's all in reference to this outcome y. So it's just y equals a plus bx, or it could be y plus y equals a minus bx. It just depends on the sign of the beta, but that's y equals a plus or minus bx is the basic equation. Well, what is b? Where does that come from? B is the breakdown of R. Okay, so R is your correlation coefficient, we recall from last week, and all B is equal to in a simple linear regression is R times the ratio of the standard deviation for Y over the standard deviation, the sample standard deviation for X. And that is all it is to convert find what B is based on R and the sample standard deviations for the dependent variable Y and the independent variable X. And so that gives you what that gives you is how much Y changes for every unit increase in X. So every time X goes up, Y is predicted to change this much. That's what B is telling you. It's sometimes also called the beta weight. It's called the weight, like a weight. It's weighting the effect of X on Y. Okay, so that's the one of the major important stats that's in the regression equation. And then you have the constant, which is A here. Now, the way that the constant is found, it's the average of Y minus the beta weight times the average of X. But the constant is on the regression line, the place where the regression line intercepts with the Y axis. And so that Y is given in the equation. Just like B is given in the equation. But to find it, that is what it's equal to. It's the average of Y minus B times the average of X. That's where the Y intercept comes from, or A, or the constant. Those all mean the same thing. Okay, so yeah, so you got the B component, the A component, the X is what you're plugging in values for, then Y is what you're solving for. So the R square, or how much the variation is being explained by the regression, is what R square is referring to. And so it's theoretically it's just the predicted variance over the total variance in the regression. And so to find it, this is what it would be equal to mathematically. To work that out, it could be done with not too much terrible effort if you just have one independent variable and a dependent variable. But that tells you, this R square stat tells you how much of the variation in some outcome can be explained away by some independent predictor. And so the variation in future arrests, at least 50% of it, for example, might be able to be explained away by the number of prior arrests that people have. So you're able to predict the likelihood of a future arrest based on someone's prior arrest to a significant degree. All right, so we'll go through all of these stats when we see it in the SPSS output. I'm just showing you here in this PowerPoint so you can see where they're coming from. All right, so this is the data that I'm going to cut and paste and put it right into a new SPSS data file. And so because I've already messed around with this, I realized that for whatever reason, it wants me to cut and paste it and put it into just like a Word file first before it allows me to paste it into Microsoft SPSS. So what I'm doing, I'm copying, I'm going to paste this into a blank Word file like this, and then I'm going to copy it out again. And let me stop sharing here, and then I want to go to let me go to SPSS, and I want to open up a new data file, and I'm going to data view, and I want to see, hopefully let me just, paste it in there. Yeah, so I cut and pasted it from the SPSS, from the PowerPoint. I cut and paste it from the PowerPoint into a Word file first, and then I pasted it into SPSS. For whatever reason, it was being difficult with me when I was trying to cut and paste directly from the PowerPoint file. So if you're having problems with that, try pasting it first into a Word document or some other document, and then cutting and pasting it from that document into a new SPSS data window, data file. So we've got these two variables here, and this is variable 1 is the number of prior arrests, and variable 2 is the number of future arrests. What we can do, just so we keep our story straight here, we can change this so it says, say, prior arrests, and we'll put future arrests. Okay, and so we're changing that so we can see this more clearly, what we're going to be doing in the regression. And what we want to do now is we want to look at the regression of future arrests on prior arrests. That is, you're using prior arrests as a predictor of future arrests in the simple linear regression. That's what you're doing here. And so what we want to do, we want to go up to where it says analyze, and we want to go into where it says regression. Okay, so note that there are lots and lots of regression options. Simple linear regression is the basis upon which lots of other regressions are further developed. Now, there are other estimation techniques, but this is called ordinary least squares regression because it's trying to fit the line that minimizes the square difference of the observations from the line of best fit. That's why it's linear regression or ordinary least squares regression, but it's simple linear regression because we're just using one predictor. And so you go over to where it says linear here. So regression, linear. Regression linear.
Excuse me?
Yes.
I don't think oh, never mind. I am seeing the right screen. Okay, never mind.
Okay, yeah, so what I did was, for just one more time here, because I jibber-jabbered there for a minute, you want to go from regression over here to linear. There are lots of entries here, but linear regression, we're doing what's called a simple linear regression. The estimation technique that's used to calculate beta is called ordinary least squares. And so take a look at that PDF to look at the math that goes through in calculating that. But once you know R, you can calculate beta quite quickly. So this is the linear regression window that pops up, and so we've got some familiar terms here. The labels actually make sense this time. So independent variables go here, a dependent variable goes here. So we can have any number of independent variables we want as being a predictor of future arrests, but we're doing a simple linear regression, so we just have the one prior arrest going in there as a predictor of the dependent variable, which is future arrests, okay? And so I'm putting that in there, and I think I want to come over here also and hit statistics. And I want to get descriptive statistics. I want to pick that just because for the purposes of our exercise, we're going to need descriptive statistics to answer one of the exercise questions. There are additional statistics that you can request. One of the things that the book shows is testing for that the errors are randomly distributed, that there's no pattern to the distribution of errors. That's called homoscedasticity. And that can be done quite easily by doing the residuals, the Durbin-Watson test. That is shown in the video that I have posted, but also you can show it graphically. I'm not going to ask you to do any tests of looking at the residuals, looking at the errors. So we don't have to worry about that, but that is something that the book highlights, and it's also in that video that is posted on Moodle that goes into some additional tests of the regression assumptions that for the purposes of this class, we're not going to get into. So, but we do want descriptives to be clicked. And then the other stuff that was already there, the model fit and estimates are there by default. Okay, so all you're doing is coming here and clicking descriptives. All right, so this is all we need to do then. We just need to put our prior arrests as independent variables, as independent variable, the future arrest as the dependent variable, and we went into statistics when we clicked descriptives, and those other two were there by default. And we want to go ahead and hit OK. All right, and let me stop sharing this for a second and go back to my other screen. Okay, and so you're going to get this is a printout. But before I do go into this, I want to first take a look at the regression line in a graph in SPSS. So although I'm not asking you just to do this for homework, I just want to show you visually what this would look like looking at the relationship graphically between prior arrest and future arrest. So we want to go up to Chart Builder. And you can play with this at home and see what you can come up with. I'm not asking you to do this homework again, but I'm just doing this as a demonstration. So when you go into this, you can go into where it says scatter or dot, and you can request right here. This is the scatter plot with the line of best fit that's going through it, and then you can drag it over there. And so on our x-axis, that's the independent variable. So we want to put our prior arrest there, and then the y-axis over here, this is the dependent variable. And so we want to put future arrest there. Oops, future arrest there. And then we go ahead and hit OK. And so we'll just examine this first. Where my line of best fit is not posted. Let me see. Did I forget to do something? Let's see. Oh, wait. I'm not sure why it's not giving my line. But anyway, this is, we're looking here at a scatter plot. Looking at the correlation here between prior arrests and future arrests. And so you can see the scatter plot is showing an upward trend in the data points. And so we know just visually inspecting it that this is definitely a positive correlation. Just exactly how strong it is, we can check that out here in a moment. But that's showing the scatter plot between prior arrest and future arrest. Okay, so when we are coming up to look at what it gives us when we went in to do a simple linear regression. First, we request descriptive statistics. That's the first thing it prints. And so here is the average for future arrests, here's the average for prior arrests, and here's the respective standard deviations. Here it's giving you a correlation matrix, a correlation between between future arrests and prior arrests, and the correlation is a 0.703. So it's a strong positive correlation. It's showing us a one-tailed test instead of a two-tailed test. I'm not sure why it's doing that. Usually the two-tailed test would just be the double, that would be 0.24 as the significance test rather than 0.12. But anyway, it is statistically significant. But this is just showing you what the correlation, the flat out correlation, what R would be, which we've done that already. That is not what we are precisely interested in here, though. What we want to take a look at is when we come down here where it says model summary. Okay, so let's talk about that last thing that I mentioned on the slideshow first, that R squared stat, that coefficient of determination. So we come up here, we see just flat out R, right? So that is in a simple linear regression, R in a simple linear regression is the same thing as Pearson's R, the thing that we already did. What R square is showing you is the square of that. And so that turns out to be 0.494. Now the R square is the thing that tells you how much of the variation in future arrests is being explained by prior arrests. So it's telling you that about 49.4% of the variation in future arrests can be explained by prior arrests. So a 0.494, it can't get any higher than 1. So a 0.494 is telling you about 49.4% of future arrests, the variation in future arrests can be explained by variations in prior arrests. And so the R square here is kicking butt. It's pretty strong. That is, if you know how many priors somebody has, that says a lot about the risk that they will be rearrested again in the future. Okay, just layman's terms. That's what that's showing. But there is at least a chunk of it, a good chunk, another half of it, the variation in future arrests that remains unexplained by priors. So that just shows you that other things are going on in people's lives that may lead them to get rearrested versus not. But nonetheless, it tells you the R square. It's telling you that almost, 0.5 would be 50%. So almost 50% of the variation in future arrests is being explained by prior arrests. With some of this other stuff, we're not going to go over that right now. This is later when we get to multiple regression. But for these purposes, the explained variation in the dependent variable is R square. So prior arrests explains about half of the variation in future arrests. I want to skip over this ANOVA test for the time being. It does produce for you an ANOVA test that's basically the same thing that we did with the ANOVA, the one-way ANOVA. So we'll come back to that. That's useful for other purposes when we get into multiple regression. But what I want to get down to is down here where it says coefficients. Okay, so this is where the values for the actual regression model come from. Okay, so our regression model is y equals a plus bx. Okay, so the constant is a. So right here, this 2.088 is a. That's the constant. So we need that value. So note that the constant is a. So that in this regression equation, the constant is 2.088. So the regression line starts, if we're plotting this, the regression line starts, if a line was plotted, it starts at somewhere around a little bit over 2 arrests. So the regression line would start like right down here. And so that's A. And then the beta coefficient, or the beta weight, the thing that x is multiplied by, is right here. This is 0.645. And so B, or the beta weight, or the beta coefficient, this is here. It's 0.645. Okay, and so those are the only 2 numbers that you need to pick out of that printout, that particular printout, in order to solve for the regression equation. And so we will talk about, this also, of course, gives you a significance test, and it, by the way, it is statistically significant. Prior arrests is, but for right now, let's just focus on how we say statements like, for a given number of prior arrests, how many future arrests can we predict? How many future arrests can we expect? Okay, so what we need to do is we just need to solve for y by plugging in these values for a and for b in the equation, and then plugging in a value for x. Okay, so in the assignment, I've got you guys answering some questions about this regression, and and I want to go to those right now to take a look at that. Let me pull this up. Okay, just a moment. Should pop up now. Let me see if I can. Right. Okay. So yeah, what I'm asking you all to do for the in-class exercise is you want to know what the predicted number of arrests is for someone with the average number of prior arrests. And then I want you to do the same thing, but for 1 prior arrest, and then for 5 prior arrests. Okay, so this is done pretty easily. So what I have right here, and tell me if you can't see my screen anymore, I just switched to Google, and I just typed in the regression equation, the parts that we need. And so right here, I've got 2.088 in my Google search bar. That's A, that's the constant from the regression equation, plus B, which is 0.645, which is beta, which is from the regression equation. And then I have it being multiplied by x, by some value x. And that's where we have to decide what value we want to plug in for x. And I said, let's say we want to know what the future number of rests is for someone with the average number of priors. Okay, and so we know what the average number of priors are because we requested a descriptive statistics for the average number of priors. And let's just go back to that real quick. It is listed right here. And so the average number of priors is 5.6. Okay. So what we have to do then is we need to go back to our calculator. You can do this on a I'm just doing this on Google, so it's people can see this. So you should be able to see my Google screen. I'm just going to type in 0.56 here, and yeah, you just have it in parentheses right next to the 0.645, and it just knows to multiply. An asterisk between that would also work. And you just go ahead and hit enter. And what you just did there, you solved for y. And so what is the predicted number of future arrests for somebody who has the average number of priors, which happens to be 5.6 arrests? It's 5.7 arrests, as the average actually tells us in the descriptive stats. Now, sometimes it will be, often it can be off if you have a large number of data that you're observing. But in this case, it's right on the money with the predicted, or with the actual observed average for y. And so that's how you answer that one. And so if you want to know the predicted number of future arrests for somebody with one prior arrest, it would just be, you're just replacing the 5.6 with a 1, because for one prior arrest, because our independent variable is number of prior arrests. So we're switching out the average number of priors for one prior and saying, okay, well, what would it be then for somebody with one prior? And so they're expected to have 2.733 additional arrests. So almost 3 additional arrests you can expect for somebody in this data set with one prior. And so if you want to know it for 5 previous arrests, you're just switching out x with 1 for 5, so for 5 number of priors, so for 5 priors. And so you've got 5.313, so a little bit over 5 arrests can be predicted. Future arrests can be predicted based on 5 priors given the observed data. Okay. And so that is what we're doing with simple linear regression. With just one independent predictor in the equation, we are going through and plugging in values for just one x value, and that's getting multiplied by the beta weight, the beta coefficient, which is 0.645, and it then added to that is the constant, and that's where the regression line starts in a graph. And so everybody, you can think of it like this: everybody starts with at least 2 arrests, and then it goes from there. So everybody in the data set is expected to have at least 2 future arrests, and then the risk goes up from there based on the number of additional priors they have. So that's what this is. That's what the regression line is the equation is communicating to us here. And let's go back then to the actual SPSS printout. So when we look then at this back here, okay, remember this is A, 2.088, this is B, 0.645. Is this a statistically significant effect? Yes, it is. There's actually a t-test for beta. It follows a t distribution, so it uses the t-table. And here's the t-test itself. And is this different than what we'd expect at random. Yes, it is. The significance here at the level is the p-value is 0.023. And so that's smaller than the cutoff point of 0.025. And so you can conclude that a prior arrest have a statistically significant impact on the number of future arrests. The direction is positive, and so it's a positive beta. Just like our correlation coefficients can be positive or negative, so can betas. And so this is a positive, significant effect. And the strength of the thing is you can interpret that using two different statistics. Right now, we're using what's called the unstandardized beta. We'll move to the standardized beta in the next, probably the next assignment, well, at least when we get into multiple regression. But for right now, the strength of the effect is this, is that for every prior arrest, future arrests are expected to go up by 0.645. So about 2/3 of an arrest. That's the strength of it. That's what's called the unit impact interpretation of the independent variable. So for every prior arrest, for every additional prior arrest, future arrests are expected to go up by 0.645. So about 2/3 of an additional arrest. Okay, and so that is the strength of it. That is the unit impact interpretation. It's the relative strength of priors on the dependent variable. When we get into multiple regression, we'll go to the standardized measures, which allow you to compare in more absolute terms the effects of multiple predictors on one outcome. But for right now, we're looking just at this unstandardized beta coefficient and its unit impact interpretation. That is for every unit increase for every additional prior arrest. That is how much Y is expected to go up. That is how many additional future arrests you're expected to have, and it goes up by about 2/3 of a point, or in this case would be another arrest. Okay. So yeah, this is essentially what you're doing for the homework. We want to, let's see, let's take a look at that. Where is my, oops, let me go back to this and then try it. Just a moment. Screen back in order. I'm just trying to go back to the my Moodle screen. Okay, yeah. Right. Okay, so this is the homework, and so I've got down here a data set that you should just be able to cut and paste directly from this and put it right into a new SPSS data file, and then just answer these questions. So keep in mind that I'm asking you to do simple linear regression, so one independent variable entered at a time. Just like we did in the example, don't put in gender and juvenile arrests and attitudes towards school all in there as independent variables all at the same time. That's called multiple regression. That is the next step that we'll get into. I'm just asking you to do this as a simple linear regression. So the first one would be a regression of looking at the number of adult arrests as the dependent variable, and the independent variable would be gender. And so you're looking at the effect of gender on the number of predicted adult arrests. And so that would just be a simple linear regression where you've got one independent variable, gender, as predicting the number of adult arrests. Okay, and then so that would be one regression outcome, and then you would go back and do it again, and you would switch out gender, and you would put in juvenile arrests for part C, and then you would switch out juvenile arrests and then put in school attitudes, and then switch out adult arrests and put juvenile arrests in for part D. So just make sure that you're doing this a simple linear regression for each one of these. Make sure that you're not you're not putting in more than one independent variable in the analysis at a time. Okay, so long as you do that, just one independent variable in the analysis at a time, then you're good. You cannot put any more than one dependent variable in there at a time. So if I say, what statistical effect do school attitudes have on juvenile arrests? I'm asking you to put school attitudes in there as the independent variable and juvenile arrests and in there as the dependent variable. Okay. So you're in regression, when you're looking at the effect of this on that, you're saying what is the effect of the independent variable and the dependent variable. That's just the typical kind of way it's described. And I'm just asking you here to report on the direction, the strength, and the significance of the betas of what we looked at. You're not doing much more than that. Well, except for the last one here, I am asking what is the predicted adult arrest count for someone with a juvenile arrest count of 8? Okay, so for that part F there, that's where you got to use the regression equation. So y equals a plus bx. You got to use that equation to do that, and you're plugging in the value 8 for the number of juvenile prior arrests. And so that's all, folks. That's what we're doing, and so that's pretty much everything we just did in class. I encourage people to attend Friday's homework session. So we're going to be working on this. But anyway, this is going to be due on Monday, and so yeah, you just need to cut and paste just the numbers into the SPSS. As to, you can make up labels yourself if you want. For the variables, you can name them if you want, but you just need to answer the questions. And so that's what you got to do. That's all for today, folks. If you do have questions about any of this, we just went over, we covered quite a bit. Stick around and ask some questions. But if you want to get started on this, that is fine. Go ahead, but we will do a session on Friday. Okay, but that is all for today. All righty.